Hi everyone, it's Professor Moser. I just wanted to go over some of the additional practice on the factoring worksheet that was given as a handout. Again, hopefully this extra practice will kind of help y'all learn this very important topic of factoring. So what I'm going to do is kind of go through each of the problems, and they're kind of organized by the different types we learned throughout this chapter. The first type was factoring out the GCF, which no matter what method of factoring you're going to do, should be the first thing that you're going to look for. So in question number one, if I look at the two terms here, we would first want to look to see, do they have any common factors? And they do. Both of the number terms have a 5. So 5 is a common factor of the coefficients. And both of them also have a x variable in common. So you can always pull out the lowest common power of x. So we recognize that the GCF is 5x. From there, we're now going to take and factor out this greatest common factor. If I factor out the 5x from the 5x squared term, the 5 will be gone. We're taking out 1 power of x, but we should still have 1 power of x remaining. And then plus, if we factor a 5 out of 30, that's going to be 6. The x term is coming out, so there's no more x term left. And so our final answer in factored form would be 5x times x plus 6. One of the things that's nice about the process of factoring is you can always check your answer by distributing or multiplying it out to make sure that you recover the original expression. If I take 5x and redistribute it, 5x times x is 5x squared. 5x times 6 is a positive 30x. And sure enough, it does match up with what I started, so we know that we did find the correct answer. Let's take a look at the next one. We want to begin by looking for the GCF. And again, there is a GCF. The coefficients are all divisible by 9. And x squared is the smallest power that's common to all of the variable terms. So we're going to factor out the GCF of 9x squared. When we factor the 9x squared out of the first term, we're going to be left with a 2x plus, when we factor a 9x squared out of the second term, we're going to be left with a plus 3. So the final answer should be 9x squared times 2x plus 3. Let's do another one. In example 3, we have coefficients of 27, 9, and 81. Their greatest common factor is the number 9. Every single term, so there's 3 terms here altogether, and notice that every single one of them has at least 1 power of x. So we can factor out an x. And then the smallest power of y that's common would be y to the second. So the GCF is going to be 9xy squared. And then we're going to go ahead and factor that out. Keep in mind that when you're factoring out a GCF, if you start with 3 terms, then you should have 3 terms in the factoring grouping from when you pull it out. If we factor a 9xy squared out of the first term, we're going to be left with a 3xy minus, when we factor it out of the second term, notice that we're pulling out exactly everything that we have there. So the only thing that's going to be left as kind of like a placeholder, 9 goes into 9 one time, so we just have a 1. And then plus, when we factor the 9xy squared out of the next term, we're going to have a 9xy to the third. Again, if you're uncertain, it's not a bad idea. You can always redistribute this back in and check to make sure that you recover the original. Let's take a look at the next one. In example 4, the GCF is going to be a 5x squared. However, we talked about this before, that whenever the leading coefficient is negative, it's always a good idea to factor out a negative as well. So for this one, we're going to factor out a negative 5x squared. Negative 5x squared factored out of negative 5x cubed should leave us with a positive x. Negative 5 divides into positive 40. That goes in negative 4 times. And then that's it. So our answer is negative 5x squared times the quantity x minus 4. The next type of factoring we came to was factor by grouping. Technically, because of the use of the parentheses, we technically have two terms here as it's written. We have this first term, which is separated by the second term by this addition sign. And if we look at the two terms that we have, both of these terms have a common expression in them, namely the x plus 1 part, okay, not the 7. So because of that, because that x plus 1 quantity is common to both, we can actually factor out x plus 1. I'm going to put a parenthesis here. When you factor out, or when you remove the x plus 1 from the first term, what's going to be left over is going to be an x squared. And when you factor out the x plus 1 and remove it from the second term, what's going to be left is a plus 7. So the final answer, when we do a factor by grouping, we get x plus 1 times the quantity x squared plus 7. Let's take a look at the next example. Typically, a hallmark and an idea where you want to look for factoring by grouping is whenever you have 4 terms. So whenever you have 4 terms, that's when you want to possibly consider doing a factor by grouping. We should always begin, though, by checking for a GCF. And in this case, if you look at the 1, 2, 3, 4 terms that we have, there's nothing that they share common other than a factor of 1. So unfortunately, we cannot pull a GCF out of this. There's nothing to really factor out. So I noticed now that there is 4 terms. So factoring by grouping might be something that we're going to try. And to do that, what you should do is group the first 2 terms together, plus, and then I'm just going to group the second 2 terms together. And then within each grouping, factor out the GCF from each grouping. In my first parenthesis, I see that both of these terms have a common factor of x. So I can pull it out, and I'm left with the y plus 6. Plus, if I look at my second factor, my second grouping, they have a GCF of 2. So I can factor 2 out of both of those. That will again produce the quantity y plus 6. We've effectively now written it as a collection of 2 terms. We have a term here and a term here. And if you notice that both of these terms have that quantity y plus 6 in common. That makes y plus 6 a common factor. So we can factor out the y plus 6. When you remove it from the first term, we're going to be left with an x. And then when you remove it from the second term, we're going to be left with a plus 2. And that gives us our factorization, y plus 6 times x plus 2. Let's take a look at example 7. Here, once again, there is no GCF, though you should look for it in the beginning. There's nothing that all 4 of those terms have in common other than a factor of 1. So we can't pull out a GCF. The next thing we're going to do is go ahead and try to group them in groups of 2. And that's kind of the thing you're looking for. If you have 4 terms, consider a factor by grouping. So I group the first 2 terms and the last 2 terms. In the first grouping, I can factor out an x, and that will leave us with an x plus 3. In the second grouping, I can factor out a 5, but in particular, again, because the leading term is negative, it's a good idea to factor out the negative of that GCF. If we factor out a negative 5, that will also leave us with x plus 3. So that quantity, x plus 3, is a common factor now, and we can pull that out, and we'd be left with an x minus 5. So we get x plus 3 times x minus 5. Let's take a look at the next one. There is no GCF, nothing that's common to all of these, so we can't do anything there. We do have 4 terms, so let's try again to do a factor by grouping. Plus, So I always do it by putting two grouping symbols with a plus sign in between, and then just plugging the terms in as you see them into each grouping symbol. Out of the first grouping, we can pull out a factor of x squared that's common. That will leave us with a 3x minus 2. Out of this term, there's a GCF of 2. But again, because the leading coefficient's negative, let's factor out a negative 2. If we do that, we're going to get a positive 3x minus 2. And now the two terms we've created both share a common factor of 3x minus 2. So we can factor that out, and that will leave us with an x squared minus 2. And that would be our final answer for this one. Okay. The next step we come to is trinomial. So tri meaning 3. This is when we have a 3-termed expression. In order to factor this one, the factors, the way that it works is the first factor has to be something that multiplies to give us x squared. That's going to be x and x. Notice that if both of these signs are positive, then both of these signs have to be positive. And then the last numbers have to be numbers that multiply to give 8. But in addition, they have to combine and add to give the middle term, which is 6. That combination of 2 times 4 will give us the 8, but also 2 plus 4 gives us 6. So it should be x plus 2 times x plus 4 is the correct factorization. We know that multiplication is commutative, so you could have even written your answer as x plus 4 times x plus 2. Either one of them would have been the correct answer. Okay. Again, especially when you do trinomials, if you feel unconfident with these, it's a good idea to check it. In order to check this, keep in mind you need to use the distributive property. Some of you might be calling it FOIL, but let's check this. If I multiply this out, does that really give us x squared plus 6x plus 8? Well, x times x is x squared. X times a positive 4 is a positive 4x. 2 times x is 2x. And 2 times 4 is 8. We can combine the middle terms to get x squared plus 6x plus 8. And that's exactly the thing that we started with. So that checks us and lets us know that we did do the correct factorization. Okay. Let's take a look at another one. Here we want to factor this trinomial. So I'm going to start by making a double parenthesis. It's going to be x and x. Anytime the last term is positive, to get a positive, that's essentially going to tell you that your two signs have to be the same. Okay? Now, that means they could either both be positives or they could both be negatives. But in order to make a negative middle term, that's essentially telling us that our middle terms are both going to have to be negative. Now, from there, there's a lot of factors to get 6. You could do 1 and 6 and 2 and 3. Because we're using factors that have the same sign here, the way these factors are going to combine is they're going to add to give the middle term, right? You can also think of an alternative list here where you have like a negative 2 and a negative 3, and the combination that's going to add to make a negative 5 would be negative 2 plus negative 3 would add and combine to get the middle term of negative 5. So it has to be an x minus 2 and an x minus 3. Okay. Or again, if you had it switched, it's the same thing. You could even do x minus 3 times x minus 2, and it's the same answer. Let's take a look at number 11. We have x squared plus 2x minus 35. So we're going to, again, factor this trinomial. It's going to factor as x and x. Anytime the last sign is negative, we have to have a mixture of signs, because the only way to get a negative is we have to have one positive times one negative. If I write out the factors of 35, They are 1 and 35, 5 and 7. But what happens this time is, and actually I could write factors of negative 35 because our last term is a negative 35. So it could be negative 1 times 35, or negative 5 times 7, or you could have 1 and negative 35, or 5 and negative 7. And these have to add or combine to give a positive 2. Well, the combination that's going to add and give a positive 2 is this one right here. Negative 5 plus 7 adds to give positive 2. So that tells you that the 5 has to go behind the minus sign, and the 7 has to go behind the plus sign. So we get as our factorization x plus 7, x minus 5. Very similarly, if we look at this one, it has to be an x and an x. Because the last term is negative, we need to have a mixture of signs. The factors of that last term, the factors of that negative 10, are negative 1 and 10, negative 2 and 5, or you could have 1 with negative 10 and 2 with a negative 5. We need to create a positive 3. The combination that's going to add to give us positive 3 would be the negative 2 with the positive 5. That makes positive 3. So the 2 has to go behind the minus sign, and the 5 has to go behind the plus sign, and that gives us our factorization. X plus 5 times x minus 2. So in essence, these last couple were the easier versions of factoring a trinomial, where the leading coefficient for these was equal to 1. It becomes a little bit more involved when your leading coefficient is not 1. Okay? And for that, you can either use what's called the trial and error method, or you can use the AC method. Okay? Trial and error method would say the factors of the first terms have to give us 3x squared. Well, that's going to have to be a 3x with an x. The factors of 28 are 1 and 28, 2 and 14, or 4 and 7. Okay? Notice the signs here. If the last one is positive, that tells us that both of these have to be the same. But in order to get a negative term, that means that they both have to commonly be negative. And then it's not just the factors of 28 now to make 20. It's the factors of 28 in combination with a factor of 3 and 1 that we need to use to make 20. And the right order and the way this should go is it's going to have to be a 3 times 2 to get 6, and a 14 times 1 to get 14, and then the 6 and the 14 will give us a 20. Okay. So if you've done a lot of these, you can get pretty quick at it and do them like this. However, there is a more systematic approach in order to do these, which is called the AC method of factoring. And let me work through and I'll get to the same answer, but by using the AC method. The AC method says you look at the coefficient of the x squared term. That's the number we call A. And you look at the coefficient of the constant term, which is the constant 28. And in the AC method, what you do is you multiply those two numbers together. So A times C is going to be 3 times 28. And 3 times 28 should be 84. What we now do is we're going to list all of the factors of 84. They are 1 and 84, 2 and 42, 3 and 28, 4 and 21. 6 doesn't go into, I'll take that back. 6 does go into it. 14 times. 7 does. 7 goes into it 12 times. And then 10 doesn't, 11 doesn't, 12 does, but then we start to get the list in reverse. But that's not the only way to get a positive 84. We could also have negative 1 and negative 84, negative 2 and negative 42, negative 3 and negative 28, right, to get positives here. So both of these could be negatives, or negative 7 and negative 12. And then what you're looking for is which of these combinations has a sum of factors that adds up and gives us a negative 20. So if I'm looking to get a negative 20, I can use negative 6 plus negative 14 to get negative 20. So what we're going to do is we take this trinomial and we're going to split it apart. So I have a 3x squared here, but in place of negative 20x, I'm going to break it apart into a negative 6x and a negative 14x. By splitting it apart, by using these two numbers, I've now created a situation where I have 1, 2, 3, 4 terms, which is going to allow us to do a factor by grouping. I group the first two. I group the second two terms. We pull out our GCFs. That's x minus 2. Here you can factor out a negative 14. We get x minus 2. And now x minus 2 is a common factor. So we pull that out, and we get 3x minus 14. It's the exact same answer you get via trial and error. Granted, the factors are reversed, but it's the same answer, and this is a more systematic approach. So, in my opinion, this is the method or the factoring type that gives students the most difficulty. But if you practice with this AC method, it's pretty systematic, and it'll turn it into a procedure where if you just do step by step by step, you will get to the correct final answer. Again, the way that works is you take the A number times the C number. 3 times 28 gives us 84. You then list all of the different possible factorizations of that number. Here we get the list, and then you look for which sum of those factors gives you the middle term. Here, to get negative 20, we needed negative 6 plus negative 14. So we use those two numbers to split that middle term up into two pieces, like we did here. And then by splitting it up, that allows you to complete the factorization by using the factor by grouping method. That's pretty much how you would do these next few. I'm not going to do it with the AC method. I'm just going to kind of go ahead and do it as is. But if you're looking for this next one, it would be a 4x and a 2x, a 3 and a 1, and you would have a plus 3 and a minus 1 should be the factorization for this one. 8x squared, you'll get a positive 12x here, minus 2x will give the positive 10x, and the negative 1 times a positive 3 gives negative 3. I'll come back to 15 in a second. If you wanted to do, let's say, this one right here, we could factor it. This is going to factor as a 2x and a 4x. We're going to have a minus 5 and a minus 1 would be the factorization for this one. And again, you can do it with the AC method. Let me go ahead and I will do, let's do 15 using the AC method, because here we actually have multiple variable terms. Again, why would you want to use the AC method? Well, it's whenever you have a trinomial whose leading coefficient is different from 1. So we have a 2 and a 3. So we do A times C. 2 times 3 gives us 6. We're going to write out all of the factors of 6. That would be 1 times 6, 2 times 3. But we could also use negative 1 times negative 6, or negative 2 times negative 3. We need to choose the pair that sums up to gives us the middle coefficient, which is negative 7. And to get a negative 7, we would have to do a negative 1 plus negative 6. So we're going to use these two numbers to split apart this factor here. So instead of writing it as a negative 7xy term, we can write it as a negative 1xy term and a negative 6xy term, like this. Okay. So we split it up. We now have 4 terms. We're going to do factor by grouping. Out of the first grouping, we can factor out x. We will have a 2x minus y. Out of the second grouping, you can factor out a negative 3y. That should give you a positive 2x minus y. And now both groupings share a common factor of 2x minus y. So you can factor that out. When you pull the 2xy out of the first term, what's left is an x. And when you pull it out of this term, what's left is a minus 3y. So we have x minus 3y. In the next set, we come across the special factoring types. One of the popular of which is the difference of squares. A squared minus b squared factors as the product of sum and difference. This factors as a plus b times a minus b. So you want to view these as something squared minus something squared. A good giveaway here when you have a difference of squares is you have just two terms and the numbers on either side of the subtraction are perfect squares. So this one should factor as an x plus 2 times an x minus 2. If we look at example 18, this is another difference of squares. The thing you'd have to square to get 81x squared would be 9x. The thing we would have to square to get 49 would be 7. So this should factor as 9x plus 7 times 9x minus 7. Here's another difference of squares. To get 25x squared, you'd have to square 5x. To get 4y squared, you'd have to square 2y. So this should factor as 5x plus 2y times 5x minus 2y. We come down to the next example where it looks like we're back to trinomials, and we are, but one of the things you want to be on the lookout for is if you have a perfect square trinomial. So these are of the form a squared plus 2ab plus b squared. They factor as a plus b times a plus b, where the factors are identical to each other. So you can write it as like a plus b quantity squared, or a squared minus 2ab plus b squared. Very similarly, this factors with equal factors a minus b, which is a minus b quantity squared. A giveaway or a tell that you might have a perfect square trinomial is when you look at your terms, if the first term and last term you recognize as a perfect square, that's a good hint. And then if you can recognize the middle term as twice the product of those two factors, that's how you know you have a perfect square trinomial. So for example, when I look at this one, I notice that 16x squared and 25y squared are both perfect squares. So it's reasonable to believe that this might factor as a 4x times 4x, 5y times 5y, where if all the signs are positive, then all the signs here would have to be positive. And that is true because if you look at the middle term, it is twice the product of those factors. If you do 2 times 4x times 5y, that does give us a 40xy. So that's how this one factors. You can leave your answer like this. I'm perfectly fine with it. Or you can go ahead and write it, because the factors are repeated, you can write it as 4x plus 5y quantity squared. Okay. If you don't notice this, or if you don't pick up on this particular factoring type, it's not a big deal. You can still use your trial and error method or your AC method to get the answer as well. Okay. But if you happen to notice that pattern, it will save you a little bit of time. Okay. Very similarly, you can check this one, but this one is another perfect square trinomial. I notice that the first term and last term are perfect squares. This one's going to factor as 2x plus 3y times 2x plus 3y, or you can write it as 2x plus 3y squared. Okay. And whenever you do this, it's a good idea. Make sure, check it out. Make sure you do get that middle term. If I check my factorization here, 2x times 2x is 4x squared. 2x times 3y is a 6xy. 3y times 2x is another 6xy. And a 3y times 3y is a 9y squared. These two combine to give us a 12xy plus 9y squared. So just a quick check. Yep, that's what we started with. So we know we do have the correct answer. Okay. Here's yet another one. This one will factor as 5y minus 1 times 5y minus 1. Or you can do 5y minus 1 quantity squared. So those are the factoring examples broken down by type. Now, when you're presented with a different example, or just one that's kind of out of the blue, there's a kind of a hierarchy of things you want to try first. So in our mixed type factoring here, every factoring problem should always begin by looking for a GCF. And if you look at this first one, we do have a GCF here of 5x. So I'm going to start by factoring out a 5x from both terms. That will leave us with the x squared minus 4. So we did factor this, but typically when you see the rules and the directions should be to factor completely. So you want to factor this thing as much as you can. If I look at this little term right here, well, that's a difference of squares. So that thing can be broken down even more into an x plus 2 times x minus 2, and then that would be as far as we could take it. Right? Because at this point, all we have is 3 distinct linear factors, and those things cannot be broken down anymore. Let's take a look at this one right here. It's a minor thing, but there is a GCF. Every single term here has a common factor of 2 that we can pull out. That would give us an x squared minus 16. Excuse me, x to the 4th minus 16. And this actually happens to be a difference of squares. If you look at x to the 4th minus 16, you can write that as something squared minus something squared. Namely, x squared squared gives us x to the 4th, and 4 squared gives us 16. So this can be written as x squared plus 4 times x squared minus 4. So far, so good. We have yet another one of these differences of squares that we can break down. So this will factor. This term here, be careful though. This is a sum of squares. Okay. A sum of squares does not factor. So if you have 2 squares with a plus sign in between, that we're not going to be able to break down anymore. That's just as good as it gets. Okay. But this other difference of squares can break down into an x plus 2 times x minus 2, and then we will have factored it completely. For the next one, we have a GCF here of 2 we can pull out. But because the first term is negative, it'd be helpful to actually factor out that negative GCF. If we do that, you're going to get a y squared minus y minus 56, which we can break down even more. This is a trinomial. The factors of y squared are going to be y and y. And now we need factors of negative 56. They're going to combine to give us a negative 1 here. The factors of negative 56 are negative 1 and 56, negative 2 and 28, negative 4 and 14, and then negative 7 and 8, and then it repeats. Or you can have the negative on the other factor, 1 with negative 56, 2 with negative 28, 4 with negative 14, or 7 with negative 8. And in order to get that minus 1 that we're hoping for, we have to use this combination right here. 7 plus negative 8 will give us negative 1. So the 7 has to go behind the plus sign, and the 8 has to go behind a minus sign. So y plus 7 times y minus 8, and that would be our factorization. We have a couple more. In this one here, again, we're going to start off with a GCF. The greatest common factor we can pull out is going to be a 2x to the second. If we factor out 2x squared, then we're going to have an x squared plus 14x plus 49. We should try, and we can break this down even more. This is a trinomial. It's going to factor as x and x. If both sides are plus, both have to be plus. And the factors of 49 to add to 14 are going to be 7 and 7. Okay. So you can write your answer like this. You could even note that our two factors are repeated. So you could also write it as 2x squared times x plus 7 squared as well. In 27, we have a GCF to begin with. All of these have a 4y in common, but we're going to factor out a negative 4y because the leading coefficient is negative. When we factor out a negative 4y, you're going to be left with a y squared minus 7y plus 10. That trinomial portion will factor even more as a y and a y. Because the last term is positive, that tells us that our signs have to be the same. But to get a negative middle term, they're both commonly going to have to be negative. And the factors of 10 that will give us negative 7 are going to be negative 2 times negative 5. In the last example, we do have a GCF to pull out first of 2. You get 4x squared minus 9. And now once we pull out the GCF, that remaining factor is actually a difference of squares. What would we have to square to get 4x squared? Well, that's going to be a 2x. Again, the formula is plus and minus. And then what we'd have to square to get 9 would be a 3. So it's going to be a 3 and a 3.